So yeah, we're gonna get started. So I'm gonna kind of like go through some machine learning basics, okay? And I'm gonna go through these basics in the context of a very simple setting, which is linear regression during the first time of the lecture, so the first hour. And then on the second half, I'm gonna go through neural networks, which is this very important algorithm in modern machine learning, okay? So let me get started with machine learning basics, right? Like some concepts or definitions. So what is machine learning? Basically, that's what I want to kind of like describe or argue, right? Like so machine learning is a set of algorithms that are able to learn from data, and so it's a set of which use data, right? And I'm gonna explain what this data is and so on. And what do we mean by learning? So what we mean by learning is just that a computer program or an algorithm learns from some experience E. So E, that's your data. And this learning is with respect to some task T. Okay, so that's going to be my task, and this task can be many things, like recognizing whether there's a picture of a cat or a dog, or predict the value of a function when you're doing regression, or play an Atari game, like automatically, the computer, and so on, or generate spin configurations of a lattice Hamiltonian, like what Roger was describing yesterday, predict the future of outcome of a time evolution of a quantum system, estimate probability distributions, and so on. So that's my task. So cat or a dog in a picture. Okay, or if we want, like in the context of the Ising model, is this configuration that you saw like running the experiments yesterday part of the ferromagnetic phase or the paramagnetic phase, okay? So let's say ferromagnetic versus paramagnetic. So these are examples of these tasks T, and we have, okay, the experience, the data, the task, and we also have a performance metric, P, okay, the performance. So it's basically a measurement of how good those algorithms become as you train the algorithms at doing whatever task you set out to do, okay? So cat or dog pictures, I get it right 90% of the time. It's kind of like a metric for performance, or how many, what's the frequency of like getting the ferromagnetic phase wrong when you're presented with a set of configurations and so on, okay? So so for performances, we use accuracy in the prediction, error rates, whenever you're trying to do some of these classifications, or accuracy in the prediction of a function when you're doing, for instance, regression and so on. And that's the score of a game as well, like if you're doing, say, Atari games and so on. So that's what I mean by performance, kind of like something that checks the task, right, bigger, okay. And so yeah, so let's say this is the basics of machine learning setting. Let me be a bit more detail about what I mean by this experience. E, or experience, which is basically the data sets, right? Like, and they can be either categorized as supervised or unsupervised learning, okay? And depending on what kind of experience the algorithm is allowed to have during the learning process, we have different categories, okay? So that's the idea. So let me give you some examples, okay, of experience or data sets. So examples. So for instance, when you're doing linear regression, you are given a data set of, say, in a y and x plane. So you're given a data set of points x1, y1, x2, y2, and so on, all the way through xm, ym. Okay, so that's an example of a data set which you can plot, and it looks something like this. We do it bigger. Okay, and then the task is to, say, predict for an unknown x. Let me call it xf. Do it bigger, sorry. So x, and here you have some x question mark. You want to predict the value of y question mark, okay? So that's a very simple task, but is one that exemplifies a big bunch of the ideas that I'm gonna be talking about, okay? There's also, say, a second example is like, I don't know, images for image classification, okay? So suppose you're given a set of images that look like this. This is a handwritten digit, right? Like, so some people would write it like that. Someone would write 2 like this, but some people would write 1 in a little bit of a different way, okay? When you write them down in an image, like let's say this is a 7, so I write it with the stick, but so many people write it like this. And the idea in this example is that when you're given a set of images like that with handwritten digits, so one thing that you can do is to attempt at classifying those images of handwritten digits with labels. Like, for instance, we can have a label for this digit, which is digit 1, so that's label 1. So x is going to be the image. Is there a question? No. And then you have a label y that signals what digit you're talking about, right? So you'll have x for the image and label y as to like which digit you're talking about. Okay, so that's 2 examples of handwritten digit recognition, but you can also have spin configurations, right? Like, because these are, if you want, pixels in an image, like pretty much like what Roger was describing yesterday, where you have like some, let's say for a 1 it looks like this, where some pixels are black and the rest are white, and so on. So you can think about this as also as configurations in a quantum system, so not digits, but like those configurations that you saw in the exercises yesterday. Okay, so that's examples of what people call experience or data sets, and like for classification purposes and regression. Okay, so that's 2 examples of of data sets, but let me be a bit more precise. This is the 2 categories that people use, and they're depending on the form of the data sets that you have, we can have basically 2 or 3 broad classification for different machine learning algorithms. Okay, and these are unsupervised learning and supervised learning, and then there's a third one which we're not going to discuss, is reinforcement learning. So but let me tell you first about supervised learning and unsupervised learning, okay, and their relations and so on. Okay, let me get rid of this here. So, so let me first discuss unsupervised learning, okay? So unsupervised learning is if you want a type of task and experience where the dataset contains many features, and what I mean by features is this input vectors x, so they're characterized by some vector x, and the idea is to learn useful properties of this data set of points x, I, okay? And I'm going to be more precise about it in a minute, but the idea is that by features we mean these vectors, right? Like, and so there can be either images or spin configurations, and like in general, like there's vectors that you can represent very generically, okay? And so one of the ideas that you can do with this type of machine learning algorithms is try to infer. So let's say like things that you can do with this type of algorithm and supervised learning is just if you're given a data set of images or spin configurations and so on, you can try to infer what the underlying probability distribution for those vectors are. Okay, so that's one of the most important set of tasks in unsupervised learning, and this is very useful in physics and but also in technology. So in physics, for instance, it helps us like in tasks as quantum state tomography, which is this task where you go and prepare a quantum system and then you measure it, and these measurements come with some statistics, and so you collect the data sets of outcomes of measurements on a quantum system or on a classical system, and then you're trying to infer this, which is like the equivalent of the quantum state. Okay, so that's one important task in unsupervised learning that's going to be very relevant for what Giacomo is going to talk about tomorrow. Okay, but in technology you can do many things if you know this probability distribution. Like for instance, if you have distribution over, like, say, images of people, then you can if you reconstruct this distribution and if you do it accurately, then you can start, for instance, start sampling this distribution and getting images like that are generated from like humans that do not exist. Okay, and you can go, for instance, online and check this this person doesn't exist.com, and then you'll see pictures of humans that are not humans, right? Like, this is one example of a practical application of something that people do. They're used in art, like to generate new art and so on, and they can do a big bunch of like interesting things that surprise me like almost every week. But you can, sorry? I think it's this person doesn't exist. I think if you Google it, you'll find it. But there's also more like more interesting applications for this. Like, for instance, suppose X is like the distributions over all possible credit card transactions. Okay, and if you reconstruct that distribution, then you can use it for, like, for instance, for anomaly detection, right? Like, so suppose you have this distribution over all possible credit card transactions, like the country, the address of the person that owns the card and so on, and then you create this complex distribution. Then if you go ahead and, I don't know, you lose your card and someone take it and goes to another country and then withdraws money or pays for something, so you can compute the probability of that transaction happening, okay? And if it comes low, like extremely low, like it seems like unlikely that that I'm from, I don't know, Medellin and so on, and then someone is using it to buy something that I never buy, right? Like, so the probability of that happening is very low. If you can estimate it properly, then you can use it to say, okay, this is very unlikely, so I'm going to raise a flag, and so you block the transaction. So this is how, like, for instance, people use this in banks and so on. Okay, so unsupervised learning in this setting, or in this task where, like, you're trying to infer probability distributions, very important for us in physics, and for also practical applications in industry and art and so on. Okay, so that's one task. There's also this clustering. Okay, so clustering is you take this distribution of points X, this experimental distribution, and then you want to see if you can infer some structure in the data. Like are there groups of data sets that are alike? Okay, so let me give you, for instance, one example of clustering, like just in words, which is if you take this data set of handwritten digits, how many clusters would you say we have if we take this data set? So like, let's say all possible handwritten digits, like, or single digit handwritten digits. So it would be like 10, right? Like, so if you take this data set of all possible handwritten digits and you do a clustering, then the hope is that if you plot the resulting clustering is that you will see, I don't know, in some abstract axis, you will see a cluster with like ones here written in different ways, right? You'll see twos here, and so on. But then, like, for instance, you would see 8, and 8 would be closer to, say, 2, because, sorry, I should write big. I'm forgetting. So you will see 1s here, but you will see 2s around here. And 8 is probably closer to 2s, but also closer to 5s, right? Like, because 5 is almost an 8 with some missing curve, okay, and so on. And then you will see, if you do a clustering algorithm on this data sets, you will see big, like 10 big blobs of like distributed by the way people write digits, okay? And even within one of the clusters, you will see differences, right? Like, for instance, if you do one of these famous clustering algorithms called PCA or TSNE, which I will try to explain if I have time, then you will see that even within a cluster, there's a structure. Like, for instance, some people write one like this, but some people write it slanted, right? And so you will start see the structure of that, different ways of writing ones within the cluster, right? Like, so the idea is, so that's an example of clustering, right? If you do, for instance, if you take the data set of the Ising model, like the one you were playing with yesterday, as like you sweep across the different temperatures, how many clusters do you expect? 2 phases, right? Like, so you, if you do clustering on that data set, it's pretty interesting. You will see something like this. So you'll see something like this, right? Like, so someone said 2, but you will see 3, okay? Why 3? So if you take those spin configurations, you'll see a cluster at low temperature where like this, most of the spins are up, okay? But a second cluster where all the spins are also down, because when you have the ferromagnetic phase, you can have either all spins up or down, okay? So this one will look more like this, and this one will look how? Random, right? Like, so up, down, up, and so on, okay? And somewhere like in this abstract space, we have the like critical temperature, right? Like, where like you go from the order phase all the way through the paramagnetic phase, okay? So those are examples of unsupervised learning algorithms, and there are more, like the ones that I mentioned: anomaly detection, generation of new samples, and so on. I'm just giving you like a kind of like a simple set of examples of what they look like. But let me tell you about supervised learning, which is another important category of machine learning algorithms. So let me see where I do it. Let's do it here. So what are examples of supervised learning? It's just like so it's like when the experience or the data set contains a feature like vector x, but also a label, okay, or yes, a label, right, like a y. And these are my like it has a lot more information than the unsupervised case, right? Like where you only have this feature vector xi. Okay, so this is the case, for instance, for handwritten recognition or linear regression, where like the idea is to predict, like given an image of a handwritten digit, what do you see? Is it a 1 or a 2? I mean, for us, it's very easy to understand what it is, but for a computer, this is just a bit string of, just a bit string, right? Like it's just zeros and ones, okay? For us, it's very easy. We see it as a 1, right? Like, but computer just sees like a 1, 0, 0, 0, 0, like for a big number of like pixels, right? So for a computer, like it's just not as straightforward as it is for us. So for a computer, it's like, how do you translate this into, that's number one, like in a computer, right? So that's a supervised learning task. So you're given a big bunch of images with their corresponding label. Okay, and there's a famous example or a famous data set. It's called MNIST that you can Google. Okay, and it's a big bunch of handwritten, like images of handwritten digits written by clerks and high school students with the corresponding label. Okay, and you can play with this. I think Estelle has an example, like a quick little check of like using MNIST, which is this handwritten digit data set where where the hope or the idea is that you're given an image and the task for the algorithm is to predict the label. Like that's a 0 or a 1 or a 2 and so on. So that's one of the supervised learning tasks.
Don't you need a label for and a subscript for the label too?
Sorry, that's right. That's right. So it's a data set. So I goes like from say 1 through m, where m is like the number of points in your data set. Okay, good point. Thanks. Okay, this is a second example, which is this linear regression, which I'm going to use to explain a big bunch of ideas that are pervasive, like in machine learning in general, right? Like, okay, so, but let me give you, so I give you these two categories, these two definitions, right? Like of supervised versus unsupervised learning. But I'm going to argue right now that there's no formal distinction between the two. If you formulate the two problems as inferring a probability distribution. So to do that, let me rephrase the supervised learning as inferring a probability distribution. So the idea is that you can rephrase this problem as inferring this particular distribution P of label I given vector X. So if we're solving a supervised learning problem, that can always be written as inferring this probability distribution, okay? Where like you're given image X and you want to find the probability distribution of a particular label, okay? Okay, so let me give you an example of why this is a good thing or an interesting framework to phrase this problem, okay? And it's because of the following, right? Like, so what number do you see here? Either a 1 or a 7, right? Like, so it makes sense to assign a particular probability distribution over all the sets of labels, right? Like, because you can most likely tell that this is either a 1 or a 7. Most likely a 1, I would say. So I would assign a higher probability of assigning 1 to that particular image, but 7 should have a non-zero probability, okay? And that's why we use this type of probabilistic framework for supervised learning as well, okay? But you can rephrase linear regression this way too. I won't do it, but there's a simple way of deriving linear regression out of this setting, this probabilistic setting, okay? But let me give you that, let me tell you about this idea that there's no formal distinction between unsupervised or unsupervised learning. If you think about both as inferring probability distributions. Okay, so let me do that. So okay, and the idea is the following, that the idea is that we're going to use chain rule of probability. So we have this vector x of let's say it's in R n, and we want to construct this distribution P of x. So it's an unsupervised learning problem. Okay, we're trying to infer this probability distribution, but x has n components, and you can use the so-called chain rule of probability to decompose this distribution, which is basically the product rule that Roger used yesterday, or a generalization of that. Okay, so this is called the chain rule, and it's called chain rule because you're just applying product rule many times. But let me just write it what it is. Right, just that you can write this as I over n of P xi and x1, x2 through x I minus 1. Okay, which basically means that you can transform this unsupervised learning problem that in principle was different than the supervised case where you're inferring this conditional probability distributions into a product of n conditional distributions. Okay, so basically you transform an unsupervised learning problem into a 10 or n supervised ones, where the labels are xi and the features are this x1 through xi minus 1 components. Okay, so that's that means there's no distinction, and the opposite is also true, because in principle so in principle you want to construct this, right, like P. So for supervised learning, you want to construct P given X, right? Like, but in principle, you can also construct this out of the unsupervised learning if you had access to this joint, right? Like, if you had access to this joint probability distribution, that you can learn from the data sets of labels and features, then you can in principle retrieve this through through Bayes' rule. Okay, so basically what you do is P y given X is y and X divided by the let me write it as sum over y, P, y, and X. Okay, so if you construct this distribution using unsupervised learning, then you can get this quantity in principle, right? Like, performing this sum may be intractable, okay, depending on what the problem looks like. So this is more like an in principle. Yeah.
I'm a little confused. What's the relation between the comma and the intersection sign in probability?
Yeah, so this one is a joint distribution. Mm-hmm. So it's a function of x and y, and so y and x. And this one is the conditional distribution, and where you fix x and explore what the different probabilities for y can take. Okay?
I mean, the common event y and x is often written as y intersection x.
You mean this one here?
Theory. That's the same as the comma. Right?
Yes,
Yeah.
that's right. That's right. Okay. Okay, so with that, I just conclude that there's no formal distinction between the two, but in practice it's useful to use this terminology. Okay. Okay, now let me discuss some aspects that are important, like when we're discussing this type of algorithms, but I'm going to use a particular setting, which is linear regression. So I'm going to assume this is a review, but I'll explain a little bit of the details anyways. So okay, so linear regression is we want to build an algorithm that takes a vector x in Rn, and we want to predict a function, so y is a function of x, okay? And the idea is that we presume, or we assume that there's a linear relation between x and y, okay? And so we construct a model. And this model is y equals some vector w transpose times your input vector x, okay? So I'm going to drop this, I'm going to keep it, okay? So this is also a vector, and that's my model, okay? So, so both x and w are vectors in Rn, so that this makes sense, okay? So what is the data? The experience is just a set of xi and yi, a big bunch of them, where I goes from 1 through m, small m, okay? So I'm going to rearrange this data set into big matrix X, which is n by m, and a vector y, which has n components. Sorry, m components. Okay? And the idea is, given this data set, can we fit a relationship between y and x, which I'm going to write as a one-dimensional thing, but it can be high-dimensional as well, like Rn. Okay, so that's my data set, and the idea is to find this relation, okay, a function that approximates the relation between the two variables. So you've seen this before, right? Like I think in calculus, linear algebra, and statistics. Okay, but let me just quickly review it. And we use the metric, the performance, as the mean square error, right? Like, that's going to be our performance, or the metric, right? Like, which is basically this. Mean is basically, so it's 1 over m, sum over I, yi, the prediction, minus yi squared. Okay? I'm going to introduce different, so this data set I'm going to call training. And I'm going to introduce a similar data set with the same statistical properties that I'm going to call a test set. Okay? And I'm going to explain why we need this in a bit. But it has basically the same type of structure, x and y, and a similar number of points, perhaps less points in your test set, okay? Because you want to use as much as you can this training set, okay? The idea is that then you can use this minimum square error function to train the model, to find the best line that fits the data set, So for train, and for performance, you want to use some data that you don't use, you didn't use during the training set. Okay, so you're going to be using the test set. Okay, and we want to do that because you want the algorithms on how to work well beyond the data that you have as your training. Okay, and this idea is called generalization. It's very important in machine learning. I'm going to talk about it in a little bit more. Okay, so this thing, like for the train and for this training set, you can write it this way as 1 over m, the norm of y, this vector here, minus sorry, not this one here, this one, so the predicted one minus the data, okay, which is this one here. Okay, so that's norm squared. So that's, and then what you do is you basically, you want to minimize this error, okay, on your train set. That's the idea. Let me see. So how to train? So what do we do when we want to minimize something? We compute a critical point. So we compute the derivatives and we make them 0, right? So what you do is basically take the gradient with respect to the parameters in the model. What are the parameters in the model? W. Okay, those are my like the parameters in the model I have. So x is data, y is data. So we're only left with w, right? So we take the gradient of the so-called cost function. So let me introduce that thing here. Cost function. So with respect to w of the mean square error on the training set. And we make that, we find the critical point, right? Like, so the point where the gradient with respect to the parameters in the model is 0. And then you can basically solve for w in this case. You can do it analytically. Okay? So I'm not gonna do it, but convince yourself that this is what you should get for the optimal vector. So it's this thing, it's x transpose, where x is this matrix. Okay. So let me give it a name. It's called the design matrix. So that's this x. So it's x transpose x inverse times x transpose and then y. Where this y is this vector here with m components. Okay, so that's the solution for the optimal set of weights in the model. This is this equation is called the normal equations, and you see them in statistics, in linear algebra, in calculus, cálculo 3, if I remember correctly, at least in Medellin. Probably the same, right? And okay, so that's the optimal for your like for this solution. Okay, so is it a maximum or a minimum? You still have to check that, right? Like you do that through computing the curvature. Okay, and just if you do it, convince yourself that this this corresponds to a minimum of this maximum square error. Okay, so that's my my little introduction to linear regression. But let me tell you about something that is, I mean, that affords us a little bit more than just linear regression. Okay, which is very interesting and important. Which is that you can, like, given this machinery, you can also do polynomial regression without changing anything. Okay, so let me tell you how to do it. So given what we've seen, let's do polynomial fitting. So how to do polynomial fitting given what we've seen? Okay, so we're going to introduce the so-called feature map. Okay. Feature maps. And this is pretty important in machine learning in general, okay? Which is basically you take your original data set and then you expand it, applying some transformation to it. Okay, so let me assume I had some x, which is in the real, and you want to do polynomial regression on it without changing like the mathematics or like this little algebra that I did, okay? The idea is that you can define this specific feature map, which is this vector. It's a function of your variable x, and it's basically this thing. So you can construct combinations of x and populate this vector. So the simplest combination of x is x to the power of 0, which is 1. Okay, so 1. Then you have x, but you can also add x squared, and so on. Okay, let's say all the way through. Okay, let's just do x3. So that's my feature map. So can we do linear regression on this new vector? That's the idea. And if we do, then we're getting polynomial fitting basically for free. Okay, because if you use this as your new data set, basically you construct your I with the corresponding y I, and you do linear regression, you're effectively fitting a polynomial of degree 3 to the data set. Okay, do you agree with that? So basically here y, your model is always the same, right? Like it's w times, so not x anymore, but your feature map, right? Like, yeah. Okay. So that's basically equal to what? To, let me write the components. Like the first component, I'm gonna call w0. That comes multiplied by 1 plus w1 times x plus w2 times x squared plus w3 times x3. Okay, so basically you're using what we used already, the same linear model on this feature map of the original data to get the polynomial fit. Okay, so that's the idea, like that you can do polynomial fitting with like just the linear thing. So we have to be careful about something though, which is when you're trying to fit this type of high order polynomials, you can go to 9 and 10 or whatever order you want. There's a problem called, so there's 3 concepts. So one is the capacity of the model, then there's the idea of overfitting and underfitting. Okay, and we're going to explore what they mean in this setting, in the polynomial fitting. Okay, so let me show you what I mean. So we have this data set. Of x and y. And x, let's say, I'm going to use these 2 symbols. So this is going to be training data, and circle is going to be test set. test data. Okay, and let me just draw my data set, like my imaginary data set. So you'll have okay, and some something like that. And some, let's say this one here. So this is my data set. So some of the data I'm going to use for, sorry, I should probably exchange them. So some of the data I'm going to use for training the model, so fitting the model, but some of the data I'm going to use as a test, okay, which are these little triangles. Okay, and so we have to be careful about the choice of the model, right? And by that I mean the capacity of the model. So that's the concept of capacity that I was referring to earlier. So it's how complex is your model or your space of functions that you're trying to fit. Okay, so a constant has low capacity because it's basically this, right? So that's my say a model with very low capacity, like only W0 is your parameter. A straight line is just basically W0 and W1, so I can give you something like this. So not a lot of capacity. Parabola is probably about the right thing for this type of data set that I draw, right? Like something like that. And then if you go further, you'll be able to fit more and more complicated functions. Okay. So that's the idea of capacity. The problem with capacity is that if you have a high degree polynomial and you perform the fit, then it turns out you can fit exactly all the points. Okay? So if you have a very high capacity model, what happens is that the model will be able to fit all the points and do something that is called overfitting, okay? Because basically you're able to, that your function is able to cross exactly all the points, okay? And that's a problem, right? Like, and I'll tell you why that can be a problem. Because when you do this high order polynomial fittings, they usually fit very well the training data, but then they can be far away from the test, okay? And like I'll show you not a plot, but let me try one more. So let me try to redo the plot. So you have so test this triangle. It's an X. Circle. Something like this, right? Like, so if you use a very high capacity polynomial, it may be that you cross all these points in an uncontrolled way, okay? So all those points are touched by the polynomial that you fit, okay? But if you go and compute the error on the test set, like this mean square error that I was referring to, like this, for instance, this point is going to be far away from the actual prediction that the model gives you, okay? Here the same, right? Like this is going to be far, and this one even worse, right? And that's happened when you use high order polynomials, okay? And this one too, okay? So it means that the mean square error, the performance metric on the training set is 0 or very low, but on the test is bad, okay? It's high. Whereas when you use a low capacity function, let's say parabola, then you may not fit perfectly the training set, but the test set error is reasonable, okay? So you will see something more like for a parabola, something like this, okay? So you'll have errors both in the training and in the test, but the gap between the mean square error on the test set and the training set is going to be comparable, okay? So that's the hope. So those concepts that I mentioned are called the capacity, overfitting and underfitting. I guess underfitting I didn't explain very well. But underfitting is the case where like, the model is too simple. Like if you fit a constant to this data set, like you'll get something like this, which doesn't describe this data very well. So that's the idea of underfitting. The overfitting one is when you have a high order polynomial that goes all the way through the data set in the training set. And then those are the three concepts that I wanted to discuss.
So that practically one should aim for having a similar error in the testing.
That's right. So
Can you repeat the question? Because otherwise they cannot hear you.
okay, yeah, the question was, how do you, so the question was, so is the point then to have a model such that the mean square error on the test set and on the training set is comparable? So, and the answer is yes. And let me do a plot if we want. So in general, this is the ideal scenario, and this is the behavior of this machine learning training of the model. So here we'll have error. Here we have error. And here we have number of samples in the data. And here we have capacity, let's say, number of parameters in the model.
Here one is on the testing?
On the test.
On the test.
Yeah. So what you will see is the error on the test, if you have very little data, is big. And as you grow the number of data points in your data set, it drops, right? Like at fixed number of parameters, if you have little data, then you're able to fit very well the training set. So the error can be even 0, okay? But as you grow the samples, then you start increasing the error. And the hope, or the ideal scenario, which is exactly what you asked, is we want to make the gap between the test error and the training error to be as close as possible, okay? So this gap should be as small as we want, as we can, okay? And let me show you the error on the capacity, right? Like, so when you have at fixed number of samples or data points, so the error looks like this for the training, right? Like, so if you have low capacity, you have large error. But if you increase the capacity, eventually you can even make it 0, okay, in this setting. But for the test error is the most interesting one. Like, it looks like this, right? Because if you have extremely high capacity, you overfit to the training set, and then eventually the error can increase, okay? So there's a point in which is kind of like the optimal capacity, kind of like cap star, like the optimal capacity, where this is the sweet spot for the algorithm, for the the capacity, okay? And yeah.
What is the trying error, the test error, and then second?
Sure. So this is the test error, and this is the training one. Okay. So everything I'm telling you about in this context translates exactly the same in the unsupervised learning case, in the quantum state tomography, in all the cases. And this is extremely general and extremely important as a practitioner of in machine learning. Okay. So all these ideas are very, very important if you practice machine learning, and even if you do it theoretically, because when you do theoretical analysis of machine learning algorithms, all you care about are these performance metrics, okay? So it's a very important, so I used a very simple setting, but this whole idea is very general, okay? It applies to a big bunch of different machine learning scenarios. Yeah?
I mean, just counting degrees of freedom and call it capacity is a little simplifying things, isn't it? I mean, if I use 3 high-order polynomials, everybody knows that that's not a very good basis.
That's right.
So if you use some other orthogonal system or whatever,
Yeah.
so capacity has to be with.
No, I agree. Which brings me to the final idea, which is called inductive bias. Okay. So. Okay, inductive bias is the idea that you have to be smart about how you choose your model. Okay, so you have to. So if you pick a polynomial to fit this type of data, and then you just let it just be polynomials, then you know you'll overfit. Then there's a quote by von Neumann that he says, like, give me a 4th order polynomial, I'll make the trunk of an elephant wiggle. Okay. Which means basically, give me a powerful enough model and I'll make it do whatever you want, right? Like, so you have to be smart about the choice and the biases that the model introduces, which is often referred to as inductive bias. So I don't have time to go into the details of like this at this point. So that's why I limited myself to this simple scenario. But I agree that this is a very important point. Let me just give you a final idea before I break. When do I have to break? Okay, let me give you this final. Yeah.
This inductive bias is related to the whole hyperparameters that you select in your model.
No, it's more like a. Oh yeah. So the question was related to a hyperparameter, right? Like
yeah, if the inductive bias is only related with the weights or
no. Okay.
The set of the hyperparameter.
Right. So the question is: are the hyperparameters related to the selection of the model?
You say bias. What do you mean?
So what I mean by bias is like, given that the whole thing is an approximation, what does the model do when it doesn't have enough data, right? Like, because if you have infinite data and an infinitely powerful model, then you're okay, right? But if you have a model that has a fixed number of parameters and then you have some finite data set, what does the model want to do? What types of errors does it do, right? Like, and the errors that these models do, depend on the way you choose the model, right? Like, that's what I mean by inductive bias. Okay. Okay. So let me give you one way of trying to control this problem of overfitting and choice of models and so on, with an idea that is also very important. It's called regularization. Okay. So the idea of regularization is the following. So that there's another way of controlling the capacity or controlling overfitting by changing exactly the model's capacity, right? Like, so the idea is that we're given a learning algorithm, a performance, and a data set, right? Like, for instance, polynomial fitting, right? Like, so you have your model X, okay, and then you have a high order polynomial, let's say, and you're given some data, and so the idea is that you can change the cost function, this mean square error, and do something smart about it to control for overfitting. It's called regularization. So I'm going to introduce the idea of L2 regularization, which is the simplest way of regularizing polynomial fitting. So you have the mean square error of W and whatever design matrix you have, and we just say train. But then you control, like you add a penalty and a so-called hyperparameter times this in particular, okay? So it's your vector of weights transpose times itself, which is basically, so W0 squared plus W1 squared plus, and so on, okay? Where lambda is a parameter you choose. It's not optimized during the training part of the algorithm, so we call it hyperparameter. And this lambda is chosen to be positive, okay? So lambda is greater than 0, greater or equal than 0. And so what happens here is that, is what? Like, you want to minimize this function, but you're adding a positive term, right? Like, because this is all positive and lambda is positive. So this term wants the weights of the polynomial, or it encourages these weights to be what? To be small, or 0, right? Like, and so if you have a data set, a big enough data set, and you use this cost function and the proper regularization, what you'll see is that this fact will help you select the best model, right? Like, in the sense that it will penalize terms that you don't need in the function, okay? So if you want, this is a way of controlling for like this uncontrolled overfitting, for lack of a better wording, okay? So how do you pick lambda? So if you replace capacity here by lambda, there's an optimal lambda such that the test error is the smallest, okay? So to do this properly, what you have to do is to repeat the training procedure several times with different values of lambda until you find the sweet spot for the test error. And since this is encouraging simple models, like simple polynomials, then we would have found like a decent polynomial with the right hyperparameters such that the fit is overall very nice, okay? So if you have questions or you want to discuss this, or maybe a question from the other room, then we can take them for 5 minutes, and then, is that okay? Okay.
When you have all that data set, is on the percentage of test, data set, test for test and for training?
Okay, so the question is, when I have a lot of data and you're gonna split the data between test and training, so what's the percentage that you should use, right, of training versus test? And the answer is, there's no right answer, but there's some rules of thumb, okay, which is basically, you want your data to produce an excellent model, so you want to use a lot of training, but you also want to have a representative data set for testing, right? Like, such that what you present as your final result is significant, right? So the rule of thumb is usually 80% for training and 20%. That's a good rule of thumb. But of course, it depends on the details and the situations. Question from the other room? Yeah.
So you mentioned that it's possible to think of linear regression as fitting conditional probability distribution.
I mentioned that, yeah. I can tell you a little bit more, right? Like, so the idea is that when you're doing linear regression, you can assign a prior distribution over these values, okay? And once you have that prior, then you're fitting, you're using, so the thing is, to explain that, you need the idea of like the maximum likelihood estimation and the idea of a prior distribution. But if you do that, then you can imagine that you're fitting a distribution py given x, given some prior for like say that the error that you have on the y variable. And you set this problem as a maximum likelihood problem, and you end up with the exact same equations that I presented there. Okay, that's without assumption of any prior on the model. If you add a prior, if I remember, is a Gaussian, that is equivalent to L2 regularization. So you can even rephrase regularization as a learning of conditional distribution with a prior. Okay, if you want to learn about that on your own, like there's a very nice book. It's called Elements of Statistical Learning by Hasty. It's very well explained, and they explain all these relations between maximum likelihood, fitting data, and so on in the framework of maximum likelihood and maximum a posteriori estimation, and so on. So there's a big bunch of different ways of attacking even the linear fitting problem, okay, that are a bit more rigorous, or more statistically rigorous. Yeah.
Let's say I have outliers.
Mm-hmm.
How do I perform the training without removing those outliers?
So I didn't, and I'm not. Sorry. The question is, how do I deal with outliers, right? Like without throwing them away. Okay. So I'm not going to address that. Okay. So the assumption in this whole thing was the test set and the training set came from the same distribution. Okay, so in principle, I'm not allowed to throw any if this is true, right? Like experimentally, there's ways of like getting rid of them, but I won't discuss them now. Okay, basically, I don't have a good answer prepared for that, but there's ways. Okay. So how about we continue? Okay.
Again, so the curve that you chose when the test error is 2 rights is when the data follows the same distribution. So I don't have any outlier.
Yes, but you have statistical fluctuations. So the question is, when this curve turns back again, is it because of outliers? Is that the question? And the answer is not necessarily due to outliers, but due to statistical fluctuations in the distributions that you're trying to fit. Okay, so this situation will happen no matter whether your data really comes from identically distributed data sets. Okay. Okay, so let me go ahead because time is short and we were late. So we'll start with like one of the most important algorithms in this deep learning revolution, like the neural network, and the idea of backpropagation, which is an algorithm that people use to train these models. Okay. And I'm going to phrase the whole discussion as like in the context of supervised learning, but you can also use it for all sort of different tasks in supervised, unsupervised, reinforcement learning. So like the whole thing that I'm going to talk about is very general, but I'm going to discuss a particular model and a particular task or setting, which is supervised learning. Okay? So then. Okay, so one of the most important models in deep learning, we're going to discuss the so-called feed-forward neural network, in which the goal is to approximate a function f. For example, we can try to construct a classifier like the one I was discussing for handwritten digit image classification. So it maps x, like your image, like this high dimensional spin configuration or handwritten digit, into a label, okay? Sorry, label that I'm gonna call y. Okay, so the idea is that a feed-forward neural network, neural networks in general, they're just functions, okay? And they're functions where like x, I don't know, can be in Rn, and y can be in, I don't know, Rm, okay? So they're high-dimensional functions, okay? That's the simplest thing you can say. And they come parameterized with some set of parameters theta. I'm going to discuss what these parameters are, etc. Okay, so the name feed. So it's called the particular one that I'm going to discuss is called feed-forward neural network, and it's because the information flows through the function from x all the way through y. Okay, so it's kind of like feed-forward, like that type of idea. And there's some intermediate calculations that you, so you start from x, you do some intermediate calculations, eventually you get to compute y. Okay, so let me see. So, and what are these artificial neural networks? They're a family of models that are used to approximate functions that can take values on very high dimensional input states or domain x, and they basically represented as interconnected neurons, which correspond to nonlinear functions that, like, quote unquote, exchange messages, right? Like, so they look like this. I don't know. So this is your initial vector x. They represented like this, right? And then you have a set of interconnected neurons. Okay, so they look like this, with all these connections, and the connections represent the parameters in the model. Okay, but let me give you a precise description of what this means. Okay, so I'm gonna tell you about just one neuron now. Okay, so what is one neuron? Okay, so let me draw that. Let me, yeah. So let's do this, right? So this is my neuron, and it has a big bunch of inputs. So what I call the input of the neuron is a vector. So I'm gonna start with x. Okay, so it's a set of so x. The components of the vector is there are x1, x2, x3 through xn. Okay. And they just come to this neuron, and then you get an outcome. Okay. So this is basically isolating one of these elements in this diagram. Okay. So let me tell you what this means, right? Like, so what is let's say the output of this calculation? So I'll tell you what it is. O. So the output O that you see here is just a nonlinear function g of the following. So w through n of xi times wi plus some b. Okay? So it's basically a nonlinear function, and then basically a vector, so a dot product between your vector x input and a set of weights w, okay? And then a so-called bias term, okay? So that's what a neuron looks like. And here we had vectors, like different vectors, but in the outcome of the neural net, what you do is you basically replicate O and all the connections that you have. Okay, so this is what I mean by a neuron connected in this way. And so basically a neural net is just a big bunch of nonlinear functions applied to some vectors that are propagated in the so-called forward direction, this way. Okay. So what are examples of these functions that are popular or that are used in machine learning? So let me give you examples of G. Of this G function. There are non-linearities. So one of the popular ones is the so-called sigmoid, which is basically this function. G is 1 over...
So the WIs that we use for are your theta.
Exactly. So the question is, the Wi in this expression correspond to my parameters theta, and the answer is yes, but not just one, all of them. So what I meant by theta is all this set of connections, and in particular for one neuron, they correspond to this vector W. Okay. Yeah.
That B could be explained as a bias, like you explained earlier?
So it's just a name, but so the question is that B can be understood as a bias, and the answer is like that's the name it has, but it's basically just something you add on top of this product of X and W.
Okay.
It's called bias for some reason. I think it's related to how like neurons in the brain fire, whether the signal is strong enough or not. So you need at least some amount of voltage to excite the neuron. So they call it bias, but because of the inspiration from what happens in the neurons. Okay, but it doesn't matter. Like for us, it's just one more parameter. So B and W correspond to the set of parameters. Okay, so you have the sigmoid, which is this this function. It's basically, it looks like this. So it's very small when X is very negative. So like very tiny. Then it grows, crosses 0.5, and it hits 1. So this is 1, this is 0.5, and that's the sigmoid, and it has this idea of like neural activation, right? Like that if you have a high input, then your neuron is active, so you get 1, and if instead the whole thing is very negative, then the neuron is inactive, right? Like it's just terminology some people use, but for us it's just a function. Okay. Yeah. Question? No. But there are more, like there's some the so-called rectified linear unit. Is this thing, it's just 0 and X. So basically it's max of 0 and X. This is one of the popular ones. There's tan H, so hyperbolic tangent, and then there's one I like a lot, is the perceptron, which is basically this function. So 0 for X is 0, then it jumps to 1. Okay. Okay, so meaning that it's inactive for negative argument of the function, and 1 for positive. Okay, let me give you one little example of how this kind of like neural nets operate with one neuron. Okay, so it's very stupid, but still. So let's say that I have two inputs, x1 and x2. And one output, O. And the input is x1 can be So it's raining or not. And then that's raining is 1 and not raining is 0. Okay? Then I have x2, which is my friends are out, is 1. So that's x2. And friends not out. That's 0. Okay? And the question you want to ask is, do I want to go out or not? Okay, so that's this output. Go out or not. And that's going out, yes, is 1, and not 0. Okay, so you think about all the Fridays you've been out in Bogota, and you collect this data set, right? Like, when it's raining, I don't want to go out, but my friends are out, so okay, I go and get wet. Or maybe I'm boring and like I don't go out ever, right? like me. or you go out no matter what. Either they're outside or it's raining, you always go out, right? So you collect this data set, and so you have the situations that you found. It was raining, but my friends were out or not, and so on. And I went out or not, and so on, okay? And then you train which weights. So you will have, like, the model is this one. O is, let's say, the perceptron of W1, X1, plus W2, X2, plus the bias, right? So my personal bias is B is minus 10 or minus infinity, right? Like, so I never go out. So I don't even need to train W, okay? Also because I have my son, right? So I don't go out a lot. But some people are always out, so their bias is B is large, right? Like it's hundreds. So this function is always very positive, no matter like whether x is 0 or x1 is 0 or 1, etc. Okay, and then this function is always 1. Okay. Okay. So that's it, right? Like, but for some people, there's something in between, right? Like where you have some bias. Let's say you have a tendency to go out, but if it is raining, then this is 0. Sorry, is 1, and if W is negative, W1 is negative, it is raining, then this argument tends to be more negative, so you have a tendency not to go out when it is raining, and so on. Okay, so I should probably move faster. Yeah?
How does the neuron knows to how many neurons she is connected to in the next layer?
That's something that you fixed in your architecture. So I'm gonna so I have only 20 minutes, so I'm going to try to at least describe the whole architecture. So I'm just trying to describe what the functioning of one neuron looks like, and then I'm going to be precise about how you pick the numbers and the architecture and so on. Okay, so that's one perceptron, and then you can think about a neural net as if you want, as a set of decisions of this type. Okay, they're not exactly decisions; they're just non-linearities, right? Like so in general, it's just more complicated. This is just to exemplify that when you do processing in a neural network, you can think about it in like as a set of decisions about like what you've seen in the previous layers and so on, so that you can create very, very complicated scenarios, right? Like so you can represent extremely complicated functions using just these simple elements as your building blocks for the complex function. Okay, so that's the idea. So let me define the neural network. I think I'm not going to be able to describe this backpropagation with 20 minutes, but let me try quickly. Right, so we have an input layer, which is this vector x, right? Like x1 through xn or whatever, right? Like, and that's my my input layer. So I call that input layer. And then I have a layer of hidden neurons. So you'll have some neurons here that are all connected to each of the inputs. Okay. And so on. And you can have, so you ask, like, someone asked the number of neurons everything is connected to. That's something you fixed prior to, like, the whole training and so on. So you'll have a number of neurons in your hidden layer, and you can keep adding layers and layers of neurons. Okay. You can have some here with all these connections. And so on. And then you have, okay, so those are like hidden layers. And finally, you have an output layer. Okay, and we mentioned we had n here for Rn, and we have here m of them. Okay. So this, and then these neurons, each of them corresponds to what I explained in the, like in the previous whiteboard. Okay, so each layer is represented by a matrix of weights. So, and I'm going to label this set of weights by W, L. So this is a matrix of weights. And it's a matrix because, so when we had one neuron, we had a vector of weights, but now we have many. And so this corresponds to a matrix W. It characterizes all these weights in each of the layers. Okay? And we'll have a vector of biases. So when I describe this neuron, we had only one bias, one number, but we have now a vector of biases because I have in each layer a big bunch of neurons. So I'm going to call this bias vector B, vector. And I'm going to define a layer of, so activations, AL. Activations. And I'm going to describe or define like the arguments. So ZL, the arguments of the layer. Okay, and so let me tell you what like each of these are. So those two are parameters. So I don't need to say anything else about them anymore. But this ZL, this is a vector, is this thing, is just this is also a vector. So it's the vector of activations in the previous layer, okay, times the weight matrix at layer L plus the bias vector BL, okay. So and then we'll have the activation at layer L is just a nonlinear function at each layer, which it could be different, right? Like these neural activations can be different at each layer, like these G functions, and this is applied to the argument. So I said this is a vector, and so what I mean by applying a function f to this vector is element-wise application of the function to each of the components in this vector z. Okay? So let me just write that down. Yeah, applied element-wise. Okay? And with this, then you can compute the function that represents this thing. Okay? So let me give you one example for a neural net with one hidden layer. Okay? just to be concrete, so it looks like this. So this is X. Then you have one hidden layer, and let's say you have the output layer. Okay. So what is f of X? In this case, where f parameterized by this set of WL and BL. So what is this? Then it's just you take this input vector. So let me. So in this case, so when you start, so you label this as L is 1, L is 2, and so on. And this is the final layer that I call L. Okay. So then this one is called L is 0. Okay. And then let me tell you what this value of this function is. So it's basically so the activations at the Lth, like big L layer, right? That's the output of the function. So is so we have L is 0, L is 1, and L is 2. So it's the activation functions of the second layer. Okay, of this, yeah, this. So it's A2, right? Do you agree? Which is basically, I'm going to assume I have only one type of nonlinear function, f. And that's, so basically this, right? This is, again, f of A0, my input times W1, okay? That's, I'm computing A1. I'm computing Z1. So this thing that I'm writing here is Z1 plus B1. That times, this is the, so this bit is what? This is A1. Okay, this thing here. And that multiplied by W2 plus B2. So I close here, close there. That's my, so what is this? Exactly. And this whole thing is my A2. Okay? That's all. That's all there is to fit for neural nets. They're just like a function application after function application on the multiplications. Okay? So that's my example of a neural net. What can we do with them? We can classify numbers, we can classify Ising configurations, we can fit highly nonlinear functions, and so on, and we're going to train them, okay? And the idea is that the training algorithm to train this type of architecture relies on something called backpropagation. Okay, so let me sketch. We won't have time to go through the derivation, but let me sketch the main idea of how we train this this neural net. So we'll define. Let me see. Do it quickly.
One question: where is the x, and why do you have to make a distinction between a and f?
So x is x. I called so L0. I called the first layer, the input layer. So I replaced x by the activation in the 0th layer. So I call that A0. This is same as x. Okay. And I don't need any distinction. Like all there is just a function applied to a vector. It's just a notation that is useful to derive the training algorithms. Okay. Which let me leave this here. So we'll define a new cost function similar to the mean square error. Yeah.
I have a question in this last AL.
Yeah.
Because the F is supposed to be the activation function.
Mm-hmm.
This A must change, or
So
same L?
it can be the same function.
I mean the L, or because
Why do
The
you
goal
have an L?
is to change over the layers.
No, so I left, so the question is, why do I have L here, like in the function, right? And the answer is, I left it like with an L, just to have the freedom to have different activation functions on different layers. But you don't have to do it. So what I did in this example was to assume that the function was the same on the two layers. But you can have the freedom to have different activation functions as you go through the feed-forward propagation. Okay? Okay, let me try to explain. The last thing is, so we can define a cost function, let's say like the mean square error for your, like, I don't know, 1 over m, sum over your data set of, like, I don't know, your, like the outcome of the neural net at the end minus like the labels, okay? Something like that. And this is going to be a function of x. So let me write it. So O is going to be a function of xi minus the label that you need to predict. Either like this is a real number or a vector of real numbers and so on, okay? And then, so you define this cost function, which is basically follows the same spirit that we followed when we were trying to do linear regression, okay? Except now the function that we have, O here, is just this highly nonlinear function which is built out of my neural net and has parameters theta, okay? So the idea is that we want to do what? We want to minimize this function, right? So how do we minimize this function? So one idea is to compute the gradients of the cost function with respect to the parameters that we have in the neural net. So basically take the gradient of your cost function with respect to the parameters in the model, which are theta. And theta are what? Are like the set of matrices W on all the layers and the biases, okay? So, and then we do what? We set it to 0, right? Like, there's an issue here, right? Like, so when we did linear regression and polynomial fitting, we did the same. So in principle, up to here, everything looks exactly the same, except when you have all these chains of nonlinear functions, then it becomes really complicated to solve analytically for WL optimal, okay? So there's no way to do it basically, okay? So the question is what to do in this case, okay? So then there are techniques to do it, okay? So let me tell you about a very important technique called gradient descent in my last 5 or 10 minutes. So before that, like let me tell you just a parenthesis. So computing the gradients, which we will need for the gradient descent algorithm, relies on something called backpropagation. And I had prepared for it, but I kind of like miscalculated the time. Okay, so I'm just gonna go and explain gradient descent, and then backpropagation we can discuss offline, or you can do it on your own. It's very, very interesting. Let me tell you the idea about gradient descent in 5 minutes. So gradient descent. So suppose we have like a highly nonlinear cost function C in this high dimensional space of parameters W, okay? So I have this function C, which is defined on a very high dimensional I don't know, W1 and W2. In this case, it's only 2 dimensions, but in general, like, it's as many parameters as you have. So it's a very like high-dimensional optimization problem that we're dealing with. And suppose that this function looks like this, right? Like I don't know. Okay, and initially you don't know what the weights are, so you can set them to 0 or randomly and so on. And let's just call that my initial set of weights correspond to some values, the cost function c. Okay, it has some c initial 0. Okay, so the idea of gradient descent is that for a multivariate function f of x, where x is the parameters in the model, so for a cost function which is a high-dimensional multivariate function of my parameters, or w or theta, I don't want to confuse this, let's just call them w, where w is this high-dimensional space. So if this cost function is differentiable near a point A, so near point A in this high-dimensional space, right, like in this W, so f of that point, or c of that point A, so we say that it decreases the fastest in the direction of minus the gradient of the function at that point A. Okay. So it goes, like, it decreases faster if you can follow this direction. This is a vector, right? So that's the idea. So that if you're here at that point A, then what you do is you compute the gradient of the cost function at that point, and then what you do is you follow this direction. And we know that this direction that you follow, let's say that it is this the gradient, it follows the direction of maximum speed of decreasing the cost function. Okay. This is such that if you do the following update, let's say in W space, I'm confusing notation. Let's just call this W again. W. So at some point during the algorithm, so the value of the cost function at step n plus 1, so you do an iteration of this following thing. Sorry, this W changes using this rule, like Wn minus some gamma times the value of the function at Wn. Okay, so what you do is you take the function, which is our cost function, you differentiate it, like you take the gradient, and then you follow the direction of that gradient, or the opposite, right? Like that's the meaning of this minus sign here. And if you do this rule, if you update the weights, or like all these vectors and biases and matrices on the neural net, you're guaranteed that C of Wn plus 1 is less or equal than C of Wn. Okay, so that's the idea of the so-called gradient descent. Okay, so we start from a set of initial weights in the neural net. They can be random or they can be 0. We compute the gradients using an algorithm called backpropagation that I didn't have to explain. And then you change the weights, each of the weights in the neural net, biases and matrices, according to this rule. And then you do this on and on, right? Until eventually you hit, hopefully, the minimum. Okay. So that's the idea with this whole thing of the gradient descent algorithm. So of course there's many problems, like not all functions look convex like the one I just drew. In general, these nonlinear functions given by these neural nets are highly non-convex, so you can get stuck at a local minimum. Like suppose your initial weights are here. Okay, you start doing this gradient descent, you come here, here you get a gradient of how much? 0. It means you don't update the weights anymore if you hit that point. You're stuck here, but you want to be here, right? So what you can do is maybe start from here at random. So there's no way around this when we apply this type of algorithms. However, there's in spite of like the fact that you have like this convexity problem, this algorithm is surprisingly good. So you may get stuck in a very in actually a local minimum, but the value of the cost function at the local minima that you find when you practice is very small. Okay, so C, let's say C of this particular W star here may be very good already. Okay, for the purposes of say classifying handwritten digits and so on. Okay, so unfortunately, yeah, I don't have time to go through the derivation of the gradients which are required for the application of this algorithm, but basically you already know this, right? Like you've taken calculus and so on, and you know how to compute gradients of chains of applications of nonlinear functions. That's the so-called chain rule, right? So if you apply chain rule on this cost function, on this where always this application of like sequence of nonlinear functions, then all you need to know basically, if you want, is chain rule. Okay, so with that, let's just conclude there and take questions. Okay.
You said you have a convexity problem, but you also have a smoothness problem. The perceptron, the function isn't even continuous.
That's right.
And with a rectified linear unit, it's not everywhere differentiable.
Okay, so with the perceptron, it's true you can't use this because the perceptron basically all the derivatives are 0, right? Like because the function is constant below like negative argument and positive argument, you always get 0 and then an infinite peak delta, Dirac delta. And I agree, but for the rectified linear units, you can still do it, even though there's a kink in the. So this is the rectified linear unit, ReLU, and this is x. So it's this thing here, and then positive. So numerically, you never hit this point because you have numerical precisions in the computer. So you never have an issue.
So it's not the Bly steepest descent to the absolute value function. It's going to jagger back and forth.
Yeah, there's no problem.
You never hit the vertex exactly. But the linear approximation that the gradient is supposed to give you is not very good.
No, but like how you do it in this case is either like your parameter is 10 minus 10 to the minus 17 or plus 10 to the minus 17. Okay, and there's no problem at all. Like you can optimize this thing, and even if you have numerical, I mean this issue, if you are here, like here or here, the difference in cost function induced by like this potential problem, they go away. And actually, still in the tutorial, they're going to ask you to try this ReLU function, if I remember correctly, and you will see no problem. So I agree that theoretically this function has an issue, has a kink in the derivative, but in practice it's just no problem. But it's a good point.
No, my question is quite simple.
Okay.
Address it in less than a minute. So the idea of creating like sequentially connected nonlinear functions is very creative. So what you use is when you set up a layer, a hidden layer, you set up a function for all of the neurons in that hidden layer.
Yeah.
You use set up individually?
So you can set them individually, but in practice people just use one of them for every single node. But I mean, you're free to try anything you want.
But does it have any implications? I mean, it gets more complex, but...
No, there's no crucial implication. There was one more there, and then
I wonder about we can use a polynomial to fit our data, but if we use a neural network, where really is the nonlinearity of the model? In the neural network, where really we can model the nonlinearity of the polynomial?
yeah. So the question is, where is the nonlinearity in the neural network, right? And the nonlinearity is like in the choice of function f that I was mentioning. So one of them is actually this ReLU. So this is a nonlinear function, but you can also have this perceptron that's nonlinear, or the sigmoid. So that induces a nonlinearity. And there's something I didn't mention, but I don't have time. Maybe I can tell you quickly. Is that these functions, this neural net functions, they're universal function approximators. So it means that if you allow yourself to have like a growing number of neurons in the hidden layer, you can approximate any function with arbitrary precision. So they're very powerful. So they go beyond polynomials. Okay. And with that, let's just oh yeah, there was one more question, and then we go for coffee.
So, do you think this is basically doing regression between nonlinear functions? It's even the same objective.
Yeah.
So why is this like a revolution? I mean, what makes special this collection of functions we're describing against, say, polynomials? Why are they?
They're universal function approximators, right?
So are polynomials. No large class.
But on like
Compact set.
yeah, so that's true. That's true. But the issue is when you try in practice, this works way better, and it works. Which takes me again to the inductive bias question that you take. Okay, you can do. There are many ways of like approximating functions. You can do Fourier analysis. You can do polynomials, and they could be in principle used. It's just that if you use them, then they don't work as well. And then you take, like they took this, and then initially this, in the 80s, they didn't work as well, okay? It's just that when they started to, or when Google started collecting data, and when compute power became so strong, so that they started working. And that's around 2010, when this revolution happened. And it was basically, part was the compute power, but part was the fact that we started producing like this crazy amount of data with our phones and with our cameras. So it was a combination of the two things. So it's basically the inductive bias they bring to the table plus the availability of compute power and data. Okay, let's just go for coffee.
Okay. See.